Okay, so welcome to the last lecture. I'm sorry I can't be here. I'm going to give a brief overview of texture, and this isn't going to make anybody an expert in it. It's basically just present some basic ideas and definitions and give you the resources that if you need to uh, use some of these ideas in your research, that you have the tools to be able to find what you need. You'll notice that I am using some slides that I put together. This is material that is taken from an excellent course that Professor Tony Rowlett at Carnegie Mellon does each year or every other year on texture, microstructure, and anisotropy. I took this as a visiting student at Carnegie Mellon when I was a graduate student. And to be honest, I still use these notes, refer to these notes quite frequently. I've essentially distilled excerpts from 20-some hour-and-a-half lectures down into 60 slides. So you can imagine that I'm barely scratching the surface of what is in here. The full course notes can be found at this link. They are available to the public. And if you have anything to do with texture, I strongly urge you to go and visit them, right? I constantly am recommending this set of course notes. So I want to start with an example of why texture matters. And this is a picture of stages of deep drawing a aluminum cup. And this is what happens when you start with a random texture, right? You get these, a texture develops, and it's not particularly beneficial to the drawing, and you get a anisotropy, and you get these ears, right? Now, of course, if you continued to draw this, these would get worse, and you would have to trim a good chunk of the can off, leading to a lot of scrap. So a huge amount of this work was actually very much motivated by this problem, by how to make beer cans cheaply. Internationally, a huge amount of money was spent on solving this earring problem, and it led to the development of crystal plasticity finite elements and other simulation techniques, texture analysis tools. And the good news is we've solved this problem. We can make beer cans without needing to trim much off. Another critical issue where texture comes into play is in transformer steels. So if we look at the anisotropy of current versus magnetic field for different crystallographic directions, we see that along the 100 direction, to get the same magnetic field, we need a much higher current compared to 111 or 110, right? And so if we think about what happens if we have a much higher current, think about it the other way, right? Because the wire current's going through the transformer, you've got your coils on either side of this, but you've got your magnetic flux going here. So your higher your flux, right, the higher your current. This graph has always confused me. I always think it should be the other way around, right? So what you want is the highest flux, the highest magnetic field, while minimizing your dissipation due to current. And depending on how you process the steels, right, you could either have a rolling texture, which is random. You could have a this Gauss texture, which is 45-degree rotation, cube on edge, sometimes it's called. Or ideally, you could have a cube texture, right? So texture is an important part of the microstructure, but we sort of want to step back up and think about what is the overall microstructure? Because in materials, we're trying to always think about the relationship between microstructure, properties, and processing. Right, and so microstructure is really a super important concept. And I've sort of skirted around this issue for most of this class, right? Right, microstructure sort of originally meant anything that can be observed with the aid of a microscope, right? If we think about microstructure in a design sense, what we really want is the ensemble of the defects in the structures. What defects are we interested in? Interfaces, right? Grain boundaries, interface boundaries, dislocations, and point defects. Well, does the orientation of grains have to do with these defects that we're interested in? Interfaces, right? So the distribution of grains, of orientations, is directly going to specify our distribution of the interfaces, right? If I have a random distribution of orientations, my grain boundary space is going to, my space of possible grain boundaries is going to look very different than if I have a highly textured, right? If I have a hexagonal crystal where all the c-axis is orthogonal to the plate, to the normal direction, my grain boundaries are going to be, for the most part, tilt boundaries of the prism planes. Whereas if I have a random orientation, then I have a much bigger space of interfaces that I have to deal with, right? So texture is a super important part of the microstructure. So how do we describe the texture? We already said earlier we need 3 parameters to describe the orientation of a crystal, right? Because it's a 3D rotation, right? We need to think about where in space one particular axis of the crystal is facing, and then the rotation about that, right? And if we define our axis as a unit vector, we need 2 parameters to define the axis, because the third one is specified because it has to be a unit vector. And then the rotation about that axis gives us another parameter. So we need a 3D space, 3D description to describe the orientation of a crystal, right? So I thought it would be interesting to introduce to some people who really made a huge impact on this field. Hans Bunge, a German fellow. He passed away in 2006. I got to meet him once as a very old man. He has a textbook that developed so much of the mathematics behind texture analysis. And he has a book in German called Texture Analysis and Material Science. It's a super useful reference. A lot of it's one of those books where the appendix called Useful Mathematical Aids is twice as long as the actual book. And a lot of the theorems and ideas that he put forth in that book, in that appendix, are actually now just being developed into useful tools, such as measuring the endpoint correlation functions of orientations. Was something I spent a lot of time thinking about for my PhD work. The other person who really made a lot of the big connections with crystal plasticity and texture was this guy, Fred Cox at Los Alamos. If you have to get one book on texture, I would get Fred's book, or the Cox, Tomei, and Rudy Wenck, Texture and Anisotropy. Fred Cox was at Los Alamos National Laboratory, did a lot of work with plasticity and texture evolution. Carlos Tomei was one of the original developers of VPSC that you're using for the project problems, and he was also my postdoc advisor. And Rudy Wenck is a geologist from Berkeley who studies the texture development of rocks and minerals during in the Earth's crust. So there's a big section on geological materials. Okay, so how do we? I'm going to jump ahead. I put some slides, I think, out of order. So what do I mean? What do we mean by texture? Real fast, right? So grains with a random distribution of orientations there's no texture. There's no crystallographic preferred orientation. Texture here, we mean preferred orientation, right? And in this case, we think about a rolled BCC metal. We have a lot of grains with the 111 direction parallel to this sample normal, the rolling direction of the sheet. And so that there is a strong preferential orientation. We're much more likely to find a grain with the C-axis, the 111 axis pointed this way, direction pointed this way, than a different direction. So how do we measure this texture, right? So we want to make this quantitative, right? So the standard method is by X-ray diffraction. We measure pole figures with the texture goniometer that we'll look at in just a second. But we can, by rotating the sample, a polycrystalline sample, we can get the probability of, we can measure the intensity of different plane normals and plot them on these pole figures, and then from measurements of multiple different poles, different crystallographic planes, we can calculate a complete orientation distribution function. The technique that we're mostly familiar with is electron backscatter diffraction, where you have a polycrystal sample in the SEM, electron beam comes down, and you get a double scattering process. You get an anelastic scattering to set up essentially a white beam condition, and then an elastic scattering, and you get a electron Kikuchi pattern on your diffraction screen, where each of these bands represents a pole and the intersection represents a zone axis. And we can use This is then projected on a phosphor screen. A CCD camera is behind that. And then it goes to a computer, and a lot of them still do have CRT displays, because once a microscope's in place, it doesn't get replaced all that often. But it's hooked up to a camera, a computer that automatically can index this. The big thing in the 90s when this was developed was computers finally got fast enough and people got smart enough to think about this to have automatic indexing rather than one person doing it by hand. And what that gives you out is a spatial map of these of the grains and orientations. And this was actually the first EBSD scan ever taken by Stuart Wright. In 1993, his advisor Brent Adams was a OSU alum. He studied with John Hurth and actually received our Distinguished Alumnus Award 2 years ago, I believe. All right, but this was the first image, EBSD image ever taken in polycrystalline nickel. All right. The pole figure is classical Bragg's diffraction, but what you do is you rotate your sample in two directions so that you calculate the intensity as a function of this 3D rotation of your sample, and from that you can calculate the pole figures. We don't actually even have the capability at OSU anymore to measure X-ray pole figures. It's since the invention of EBSD, it really is a lost art, right? And so what we're interested in is the grain orientation, the distribution of our grains in our sample. This is what you may be familiar with. One way of representing texture is called a inverse pole figure. So the naming convention is a little confusing. A pole figure tells you how what directions your crystal poles or crystallographic axes are pointing with respect to some sort of sample coordinates. The inverse pole figure is just the opposite of that. It says, in this case, if I take my normal sample direction, and I project it down onto my crystal, what plane does it make an orthogonal angle with? Right? What plane will it strike normally? And in this case, this strong axial 110 texture means that my 101 crystallographic direction is parallel with my normal sample direction, right? The orthogonal to my rolling sheet. Of course, this works because it's right when I can use poles and directions interchangeably, because this is a cubic inverse pole figure, and they take a little bit of interpretation. But in this case, what this is telling me is that most of my 101 poles are roughly parallel to my sample sheet. And the color bar on this is MRD, or multiples of the random distribution. Sometimes it says MERD, multiples of the uniform random distribution. And what texture is normalized so that I can say I'm 8 times more likely to find my 101 parallel to my normal direction than I would be if it was a uniform random, if it was a non-textured sample. 8 times random is a fairly strong texture. Okay? So grain boundaries are a very important aspect of texture, right? If I have two grains, or this grain specified by orientation, this orientation GA, this one by orientation GB, I apply a rotation to GA to get me to GB, I can mathematically define this misorientation as GB GA inverse, right? And this tells me a lot of what I need to know about this grain boundary, right? What's the crystallographic relationship across it? What information it doesn't tell me is the normal to the grain boundary plane, right? I don't know whether this grain boundary is going straight into the screen or it's going into the screen at an oblique angle. So it's only half of the grain boundary information. But without actually removing material, it's very difficult to measure the full 5-parameter description for grain boundaries, right? So we have to define what we mean by orientation, right? And in this case, the orientation is a relationship between our crystallographic sample axis, our crystallographic axes, and our sample axes. If we have a non-cubic unit cell, it's a set of Cartesian vectors that we can that our crystallographic axes are defined with respect to, that are orthogonal. But it's a set of orthogonal unit vectors that define our crystallographic frame in some way. We looked at two different versions in class. We talked about the Miller indices, or the HKL-UVW, right? So we specify the plane normal that is parallel to Z, and the crystal direction that's parallel to X. X we call, by definition, the rolling direction. Z is the normal direction, and Y is the transverse direction. This comes from the problem of rolling steel and aluminum sheet. That a lot of these techniques were developed for. Miller indices are super convenient for discussing and understanding what's going on physically. They're not so easy to work with mathematically. Typically, we define things in terms of the Euler angles, or Bunge's Euler angles. And this is a set of 3 rotations to bring our crystalline sample into coincidence. And we have an animation here. So here we have our sample axes, and here we have our crystallographic axes, our 001, 010, and I said it backwards. 100, 010, and 001 are A, B, and C crystallographic directions if it's cubic. And so we have 3 angles, and the first one is a rotation about the sample normal direction until E1 and E2 are in the same plane as 100 and 010. This crazy rotation. Okay, so we do that, and then we do another rotation about the new sample direction, this E1 prime, to bring E3 prime into coincidence with our 001 sample direction. So now our sample normal direction is now aligned with our crystallographic 001 direction. And then we rotate around the new E3, the new normal direction, to bring the 100 in coincidence with the RD, and the 010 in coincidence with the TD, right? And this is just a convention, right? This is just another way of looking at it, right? And, oh, did I remove that? Why do we use Euler angles, right? And it is because that if we write things in Euler angles, there's a Fourier series expansion in terms of the spherical harmonics that can be symmetrized to reflect the crystal symmetries that are inherent in the crystal. So the reason we use these complicated Euler angles is because there's a convenient Fourier series for them. And that Fourier series allows us to do things like convolution integrals with respect to orientations, so we can write out these distributions, calculate them. It was originally developed as a way of the classic problem of inverting the pole figure, right? We had integral. The pole figures only give you part of the information, so you have to find the ODF that's consistent with those the orientation distribution that's consistent with those pole figures, and you end up with a bunch of integral equations that are much easier to solve in terms of this Fourier series. So that's why we use Bunge-Euler angles. So what do we mean by orientation distribution? I've been saying this a lot, right? But we haven't defined it, right? So it's a probability distribution over the orientation space, right? So we have an orientation space where each point in that space represents a single specific orientation, right? And we have a probability distribution that's defined on this space. So evaluating our ODF for an orientation gives us the probability of finding that orientation in our sample, right? Right. And so, right, we have to a little pedantic here maybe, but the probability density versus a probability distribution. We say orientation distribution function, really it's a density, right? It's the area under this curve that normalizes to 1. It's not the cumulative distribution function. So really when I say ODF, orientation distribution, I'm really talking about the orientation density function, but historically that the names mismatch, right? So what we get into sort of what are the difficulties of working with orientations, particularly orientation data. So if we think about the surface of the Earth, right? We think about how we would grid that up, right? We can define a distribution on the surface of the Earth, like the population, right? How the population is distributed, right? So you can imagine you're an evil being in space and you shoot a laser down onto the Earth, right? What's the probability that you're going to fry somebody? So you can think about maybe gridding up the surface of the Earth and counting the number of people inside, and then you put that on a sphere. Well, it gets complicated because we want it so that when we integrate over the entire Earth, our probability measure is 1, right? If we want it to be an actual PDF. And we can think about our coordinates. We can write longitude and latitude are two parameters that describe our coordinates on the surface of the Earth. But the amount of area that we sweep out on this surface, the surface of the Earth is a 2D surface. So the amount that we sweep out by a differential in longitude and a differential in latitude is not uniform over this whole sphere, right? So we need to introduce the concept of an invariant measure, right? We want it so that we're always sweeping out equal areas over the sphere, and this is the exactly the same as doing derivatives in polar coordinates or spherical coordinates. The difficulty comes in, this is a 2D surface which defines a three-dimensional sphere. For orientations, we need a 3D surface that defines the surface of a four-dimensional hypersphere. So it's one level more of abstraction. And so how do we visualize this? So typically we take our Euler angles and make a three-dimensional space, Cartesian space, and then make slices through them. Here we have phi. Our Euler angles, our Bunge Euler angles are to add to confusion. I missed that here in our example. We call these Euler angles phi1, phi, and phi2, because that's what Bunge came up with, and we've never changed it. We typically will plot this in the phi1, phi space, and then look at slices along phi2. And what this is showing here is that the density of points that you get if you do this for a perfectly random distribution. As phi goes to 0, your crystals will be much less densely packed than as phi goes to 90. And this is because of that invariant measure on the surface, 3D surface that defines our 4D hypersphere. So the derivatives with orientations have this sine phi term in there, right? So this is the reason why we plot things in terms of multiples of the uniform random distribution. We normalize by this to take this non-uniformity of it out of the visualization. So when you look at the orientation space, you don't have to use your mind to correct that, oh, these points are much more densely packed than they are down here. Right? And of course, we want to normalize our orientation distribution so that it equals 1. We have to take symmetry into account. I think I took some of that symmetry stuff out for this short example. But this allows us to give a sort of working definition to the ODF. Our ODF, our orientation distribution function, is f of g times dg, some small neighborhood about g, right? So if I evaluate this for an orientation and some small neighborhood about that orientation, it gives me the probability, right, the volume of grains in my sample that have that orientation divided by the volume of my entire sample. So this gives me an actual probability, right? F of dg is a probability. We can also do that with number of discrete grains in the sample, right? Essentially, what's the probability that a random grain I pick is going to have the orientation that I'm interested in? All right, and this just is how we typically display orientation distribution functions. We look at different slices in phi2. Right, here's our 3D space. We slice it this way, and we stack those slices up as either color maps or contours. Interpreting these is kind of tricky. We have different fibers, right? Different texture components in here that arise by processing, and there's a lot of nomenclature and taxonomy, right? Okay, and so here, when I say fiber, right, these are sections through. So these contours are all connected through by this line. All right, and this is a common texture component that appears in rolling of FCC metals, and it's called the beta fiber. Right, but it's tricky to think about these things in terms of a three-dimensional object, that we have this essentially cylindrical tube of high probability running through the center of our orientation space. A lot of you may be more familiar with interpreting pole figures. Going back and forth from the ODF to the pole figure is tricky. And the words that Professor Rowlett used here are also a little confusing. He says, note that any given component that is represented as a point in orientation space occurs in multiple locations in each pole figure. Basically, what he's saying is, a point in Euler space or orientation space uniquely defines a crystallographic orientation. Pole figures, on the other hand, only tell you how a crystallographic axis is pointing. It tells you nothing about that rotation. So if I only look at, say, the 001, right, there's an infinite number of ways I can have a crystal with an 001 axis pointed this way, right? All the rotations about it. But if I take 2 points on 2 different pole figures, any of those 2 points will correspond to 1 point in the orientation space. So in this case, this point in my orientation space in my beta fiber corresponds to the orientation where my 001 is pointed this way, and my 111 is pointed this way, right? Right. This point here corresponds to this and this, right? So if I only look at one of these pole figures, there's an infinite number of points in my orientation space that correspond to this point on my pole figure. If I specify 2 pole figures, this point and this point, it means I'm specifying the direction of the 2 of my 3 orthogonal directions that define my crystal. So that means I reduce it down to 1. Okay. So we talked about how texture evolves during deformation. We didn't talk about particular textures that arise. So some of the most important textures that have names, remember this happens because of restrictions, and we talked about Taylor model and the texture predictions by Taylor model a little bit. But each different set of boundary conditions is going to give us a different final texture. Each deformation path is going to give us a different final texture. And some of them that come up from common operations have special names. So here we have this wire drawing texture. right, for copper wires that comes about when you have an axisymmetric deformation, right? Meaning you're taking a cylinder, you're making it longer and skinnier at the same time. And this gives you a 111-100 duplex texture, right? Meaning that our sample normal, right? We have a large number of 1-1 crystals with 111 parallel to our sample normal, and a lot of 001 parallel to our sample normal, but very little 011, right? And how strong this texture that develops is a function of a lot of things. You can imagine it's going to be a function of the strain, but it's also going to be a function of maybe say the work hardening behavior and the recovery mechanisms that are possible that are going to affect which slip systems become, which families of slip systems become active. And what we see is if we look at how strong the cube component of that, the 100 component is, as a function of the stacking fault energy of our metal, we see that it starts out very low, goes through a maximum with stacking with silver developing an almost perfect cube texture, and then high stacking fault metals like aluminum developing a low percentage of this. And this all depends on the deformation behavior and whether you're having planar slip or easy cross slip. And it's a very nonlinear relationship. The deformation strain has a role, and this is in case copper. So copper is here. So we would expect it to be about 60% 111 and 40% 100. If we look at the 111 component, at zero strain, it starts off as 4 times random. That texture, this intensity for this region gets higher and higher and higher, and then begins to drop off again as recrystallization processes and other things come into play. Right, so we basically double the probability of finding a 111 grain, and then it shrinks again. Temperature also has another huge effect, right? If we do a drawing and then we anneal it, the temperature at which we do the annealing at gives us very different final textures. At room temperature, in this case, we have a max intensity of almost 7. As we increase the temperature, this decreases. And then once we get past 500 and start to go up again, we start to essentially eat up. We reverse the randomization. We eat up the cube component, and we basically become all 111, all 111 again. And there's a lot of questions about what are actually all the mechanisms of what's going on here. The uniaxial compression, different FCC metals, we get different intensities, right? So it's going to have to do with the stacking faults, the stacking fault energy and deformation modes. BCC materials give us different textures than FCC. No great surprise there. We have completely different set of slip systems. Right. We get right. Right. And so we can see the texture development as a function of strain in FCC copper. I got these slides a little out of order, sorry. I didn't quite want to go to BCC just yet. Composition, the alloying, right? This is a really important kind of idea that the alloy, the composition greatly affects the texture. So here we take copper and we add zinc to it to make brass. As we go from 0%, we have a typical FCC rolling texture. By the time we're at 30%, we have a very different texture that develops. Brass gives you very different microstructures under rolling than pure copper does. And it's a smooth transition from one as the other as we change the properties of our metal. Right, this is just another one. So here we are, rolling textures, BCC. Right, so this is low carbon steel. Right, there's here a lot of the, what you'll notice is the 110 BCC rolling PDF looks a lot like the 111 rolling PDF for rolling in FCC, right? In shear, you also get a completely different set of textures that come about for shear, right? They're sort of here for your reference. But there's a lot of complicated things going on, and it's a bit of a diversion to get away. Hexagonal metals, because of the various slip and twinning systems and the huge heterogeneity and resolved shear stresses, we get very different behavior. You can see under uniaxial in titanium, right, we get a prism type orientations that are favored. In compression, we have a rotation from the basal, an orientation here that is favored. If we look at zirconium versus titanium, both group 4 metals, where this peak appears is going to be different. We have slightly different C over A ratios. So where in zirconium it's much closer to basal than it is in much closer to the basal pole than it is in titanium, right? And depending on the C over A ratios, we get different rolling textures, right? If we're greater than, our C over A is greater than the ideal, we get the splitting in the rolling direction. We get 2 peaks to either side. If we're pretty close to ideal, we typically get a single basal peak. If we're less than C over A, then we get a split in the TD direction. Right? A lot of times hexagonal metals will be clock rolled, meaning that they roll the sheet along one direction, rotate it, roll it again, rotate, roll it again, rotate, roll it again, and this forces a very strong basal texture, regardless of the C over A ratio. Right? So what are the big takeaways that I'm trying to put out here? This was a lot of information. I don't expect you to be able to recall it. Everyone wants to know what is a potential question I could ask on the exam, right? And it's the takeaways that anytime you deform a polycrystal, or not even just deform, thermomechanically process a polycrystal, whether you heat it up or you deform it, you're going to alter the distribution of crystallites in your material, right? How those evolve are complicated right? But because our crystals are anisotropic, our macro scale properties are going to evolve in these complicated nonlinear ways as well. And so I guess that's my takeaway message, and we'll stop right there.
I'm sorry, Builder. I'm sorry. I didn't mean to choke, Steve.
Hi. No.
Okay. This is our office.
Oh, crap. Did I forget to hit record?
Oh, my God.